Hello, and welcome to a video where we are practicing rational functions with slant asymptotes. I'm going to let you know right now, it has been over a year since I've made a video, so there may be a few stumbles in editing or taking me a moment to choose my different colors for my writing. But anyway, let's get started. So we can see here, we're going to start by graphing this function, and we want to complete all of these different things, find all of our features, then make a table and draw the graph. So let's start by factoring and simplifying r of x. Oops. See what I mean? Okay, there we go. So when we are simplifying r of x, right now, oh, too wide. Too wide. I'm not going to edit this out. Let's make that consistency a little smaller. Okay. Much better. Okay. R of x is equal to x squared plus x minus 12 divided by x plus 2. First, we want to factor this. So our numerator will be x plus 4 times x minus 3 divided by x plus 2. I notice that nothing cancels out, which is fantastic for us, because when we are finding our domain, holes, and vertical asymptotes, I know that the answer to are there any holes is the same answer to the question, does anything cancel? In this case, since nothing cancels out, we're not going to have any holes, and I love that. So let's make a marking of that. There will be no holes, or none. For our vertical asymptote, we're going to find that by setting our denominator equal to 0. So in this case, we'll have x plus 2 is equal to 0, or our vertical asymptote is that x is equal to negative 2. What this means now for our domain, we will not have any breaks in our domain for the holes, but we will have one for our vertical asymptote. So our domain will be from negative infinity to negative 2, and from negative 2 to infinity. So again, we're going to have a break in the domain for that vertical asymptote. There we go, right here. So we have found all of the features in that first bullet point. The second bullet point is asking us to state the long-run behavior in a horizontal or slant asymptotes. Now, I've already told you that we're going to be dealing with slant asymptotes, as is the title of this video, but how do we know that we're going to be dealing with our slant asymptotes? Well, there we go. We're going to be dealing with our slant asymptotes because the degree of the numerator is greater than the degree of our denominator. So in this case, since we have a 2 here and an exponent of 1, that tells me we're going to have some type of slant asymptote. So to deal with that slant asymptote, we are going to be using polynomial long division. Now I'm going to go through this polynomial long division slightly quickly because I did actually use this problem as an example in a previous video in the bonus rational functions video of how to find a slant asymptote. It's only about 6 minutes long. If you haven't watched that video yet, I would advise going back and watching that. But this was problem number 2 in that video. So we're going to start with setting up that we have x squared plus x minus 12 divided by x plus 2. I'm going to rewrite that x plus 2. That was a little sloppy. There we go. Okay, so x plus 2. So we're always going to start by looking at the very first term. So this x, what do I need to multiply to this x to get to x squared? Oh, I'm going to need to multiply that by x. So now I'm going to take this x, so double check x times x gives me x squared. Take this x and put this out in front. We have x times whatever we're dividing by, in this case, x plus 2. So that's going to give me x squared plus 2x. Now I'm going to take these terms and subtract them. X squared minus x squared gives me 0. We've done this correctly. Then we'll be left with x minus 2x, or a negative x. And we need to make sure to bring down the negative 12. Whoops, that's the wrong color. There we go. To bring down that negative 12, and now we'll start this all over again. So we'll ask ourselves, what do we need to multiply to x to get to negative x? We need to multiply that by a negative 1. So I'm going to take that negative 1, multiply it to whatever I'm dividing by, to give me negative x minus 2, and I'm going to make sure to subtract this whole piece. Negative x minus a negative x is like negative x plus x, giving us 0. Negative 12 minus a negative 2 is the same as negative 12 plus 2, or a negative 10. Now, negative 10 is our remainder, but honestly, we don't really care. You don't need the remainder. So whatever I have left up here, this is going to be my slant asymptote, or that final answer of y is equal to x minus 1. So that's what we will have for our slant asymptote. Now, the long-run behavior for this, I've mentioned previously that the long-run behavior is always connected to the horizontal asymptote, and whatever we have for our horizontal asymptote, that's just where r of x or our y values are going, but it's a little bit different. For here, this is going to bring us back to our polynomials unit. So whatever the long-run behavior of this slant asymptote is, that is what the long-run behavior of our entire function is going to be. So I can see that this is an odd degree, or degree of 1, and a positive leading coefficient, which means for our long-run behavior, as x approaches negative infinity, or my left side of the graph, r of x is going to approach negative infinity, or it's going to be pointing downward. And as x approaches positive infinity, or the right side of my graph, r of x approaches positive infinity as well, or the right side is moving upward. So it ultimately looks something like this. I know that kind of ran into my work for my polynomial long division, but whatever we have for the long-run behavior of our slant asymptote, that is what it's going to be for our long-run behavior overall for the function. The last piece here that it wants us to find, we found our slant asymptote, we found the long-run behavior. Now we need to determine if the function crosses its horizontal asymptote. Now remember, we can have it cross the horizontal asymptote, tiptoe a little bit around. The same can be true for the slant asymptote, or the slant asymptote intersection point. So when we find this intersection point, we need to make sure, I'm going to move this up just a little bit, we need to make sure that we set our entire function equal to our slant asymptote. So our slant asymptote intersection point, there we are. So we are going to set, let's see, x minus 1 is equal to our entire function. I'm just going to set it equal to the original function, but you could do it to the factored form if you'd like. I'm going to start by multiplying both sides by my denominator, or in this case, x plus 2. So that's going to give me x minus 1 times x plus 2 is equal to x squared plus x minus 12. After I use my FOIL method for these two factors right here, or box method, we're going to get x squared plus x minus 2 is equal to x squared plus x minus 12. Now from here, if I'm going to start subtracting x squared on both sides and subtracting x on both sides, and if I do that, a lot of stuff goes away, and I'm just left with negative 2 is equal to negative 12, which we know that's not how math works. That is not what that means. So if we come across something like this, it just means that there is no intersection point, or no slant asymptote intersection point. So make sure to denote that. And that is going to be the last of that second bullet point that we have, where it's asking us to find the long-run behavior, horizontal or slant asymptote, and the intersection point. Third bullet point is asking us to find the vertical and horizontal intercepts, if there are any. That is going to be exactly the same as all of our other problems that we have practiced. So when we are finding our vertical intercept, we've already found the vertical asymptote. Oh no, that's the highlighter. Okay, there we go. The vertical intercept. Regardless of the function, we are always going to find that by plugging in 0 for x. So we'll have r of 0 is equal to, and again, you can put this into the factored version or the original version, that is up to you. I'm going to put this in the original version. So we'll have 0 squared plus 0 minus 12 divided by 0 plus 2. That's going to give us negative 12 over 2, or a negative 6. So our overall vertical asymptote, vertical intercept, is going to be at 0, negative 6. So that is going to be that first feature. The very last feature here that we're going to be finding is our horizontal intercepts. So for our horizontal intercepts, we're going to make sure that we set either the entire function equal to 0 or the numerator equal to 0. In this case, I'm just going to set the numerator equal to 0, and I'm going to be using the factored form to do that with, but you can do either. So now that we have our numerator set equal to 0, I'm going to set each of these factors equal to 0. And I'm going to solve for x. So I'm going to get x is equal to a negative 4, and x is equal to 3. So our two horizontal intercepts are at negative 4, 0, and 3, 0. So that is us for finding the rest of the features. Very lastly, we need to make a table and draw the graph. Now for the table, we're going to make sure that it includes all important points. That means vertical intercepts, horizontal intercepts, holes, which we do not have, any slant asymptote intersection points, which we do not have, as well as working around that vertical asymptote. So when we make our table, that's a little crooked. There we go, that's better. All right, when we make our table, we're gonna make sure that there's at least 3 points on either side of our vertical asymptote. So we'll have 1, 2, 3, our vertical asymptote at negative 2, and then 1, 2, 3, perfect. Okay, so let's see, we're going to make sure that we have our vertical asymptote here that is undefined at negative 2. We might as well mark that in right now. X is equal to negative 2, perfect. So when we're deciding on our table, I'm going to make sure that we're kind of close to our asymptote so we can see what's going on, really close, how close we should be getting. So I'm going to go down just half of a step, so negative 2.5, and then I'll continue with full steps, so negative 3 and negative 4. That is for our left side, and then for the right side, we're going to go up half a step, so negative 1.5, and then continue on with full steps of negative 1 and 0. At this point, I want you to fill in any pieces that you know. For instance, I know that one of our horizontal intercepts is when x is equal to negative 4. I also know that our vertical intercept is that when x is equal to 0, y is equal to negative 6. I will now also check to see if there's any points that we're missing. So I noticed that we're missing our horizontal intercept right here of 3, 0. So I'm going to make sure to include that in my table as well, just so we have all those important pieces. So now what I'm going to do is I'm going to take negative 3, negative 2.5, negative 1.5, and negative 1, plug that back into my equation, and find out the y values. I have already done that for us, so I will let you know when x is equal to negative 3, y is equal to 6. When x is equal to negative 2.5, y is equal to 16.5. When x is equal to negative 1.5, y is equal to negative 22.5. And when x is equal to negative 1, y value will be negative 12. Now, I understand based on the scaling of this graph, you're not going to be able to fit some of these points on here, and that is totally fine. Just fit what you can. With this scaling, we're at least able to fit 2 points on either side of our vertical asymptote, which is important. So first I'm going to graph these points, and then I'm going to show you how that slant asymptote kind of fits in. So let's see, we have, negative 4, 0. We have negative 3, 6. We have these 2 points right here. And then we have, 0, negative 6. And we have 3, 0. So we have these points right here, and it's a little bit difficult to tell what's happening with that slant asymptote, but I can see that there's nowhere on here where like a horizontal asymptote is going to work for us. So it has to be somewhat diagonal, which is difficult to show when I have a vertical laser pointer. So when we move back to that slant asymptote of x is equal to -1, if we use our y equals mx plus b, or y-intercept form, I know we're going to start here at -1, and that slope is going to be 1. So that slant asymptote looks something like this. And now I can really see, oh yeah, so this is where that curve is breaking up, and this is where that curve is breaking up. So drawing that slant asymptote is going to be very helpful. Well, now that we have all of our points and we have all of our asymptotes graphed, if we graph our points, it's going to look something like this. There we go. So this is an example of what a graph will look like when you have a slant asymptote. So let me get in all of our features there. There we are. So we have done quite a bit in this video. Feel free to pause, go back whenever you need. I'm going to make sure we practice some of this in class. If you have any questions, let me know. Otherwise, have a good evening.